Hey there! Tonight we're embarking on a quiet journey, following the moon's gentle pull to uncover one of Earth's most ancient and profound secrets, the science of tides. It's a story whispered by the oceans themselves, a timeless dance between celestial bodies and our watery world. It's a journey perfect for peaceful contemplation, revealing how our vast oceans move to a gravitational tune. If you find yourself drawn to these quiet moments of discovery, consider liking this video and subscribing to the Sleepless Scientist. It truly helps us share more stories like this. Now let's drift back in time to an age when humanity lived intimately with the land and sea. Imagine our earliest ancestors gathered on a prehistoric coast, their lives intertwined with the rhythm of the waves. They were keen observers, their survival dependent on understanding their environment. Day after day, they watched the ocean's edge, noticing something remarkable. The water didn't stay still. Sometimes it crept higher up the shore, engulfing familiar rocks and reaching new marks on the sand. Hours later, it would slowly recede, revealing vast stretches of seabed where food could be found. This wasn't random. It happened with a predictable regularity, a gentle inhale and exhale of the vast ocean. Early communities began to mark these changes, not with scientific instruments, but with simple observation. Then a profound connection began to emerge. As they watched the ocean, they also watched the night sky. The moon, a constant companion, seemed to influence the water's dance. They noticed that the highest tides often coincided with the full moon and again with the new moon. The lowest tides, too, seemed to follow the moon's changing phases. This intuitive link, though not yet understood scientifically, was powerful. It sparked wonder and perhaps a touch of trepidation at the mysterious force moving such immense bodies of water. To explain these grand movements, myths and legends began to emerge from every corner of the world. The ocean was not merely water, it was alive, breathing, or moved by powerful deities. Some tales spoke of colossal sea creatures inhaling and exhaling, their breath causing the water to rise and fall. Others described celestial beings pulling the waters with invisible threads. From the Norse sagas of the Midgard serpent to Polynesian legends of Maui fishing up islands, the human imagination grappled with the ocean's rhythmic power, weaving stories that resonated deeply. But beyond myth, practical knowledge was essential. Early mariners and fisherfolk, their lives dependent on the sea, started to develop empirical understanding. They learned when the tides would be high enough to launch their boats and when they would recede, leaving valuable fish stranded in shallow pools. For navigation, knowing the tides meant safe passage through treacherous channels and avoiding being stranded on sandbars. This knowledge was precious, passed down through generations. They began to mark the highest and lowest points the water reached, perhaps using stones or notches on coastal rocks. These simple records were the first steps towards a predictive system. The moon's position became a key predictor. They observed how the moon's height in the sky, its phase, and even its apparent path influenced the timing and height of the tides. This wasn't theoretical physics, but a lived science, deeply ingrained in their daily routines. It was a testament to human ingenuity and our innate drive to understand the world around us. The whispers of the shore, the rhythmic ebb and flow, became a natural clock, guiding their fishing expeditions, their travels, and their very survival. These early observations, though rudimentary, formed the bedrock of our understanding. They were the first threads in a vast tapestry of knowledge that would be woven over millennia. The moon's quiet command over the oceans was felt, respected, and empirically charted long before gravity was a concept or celestial mechanics was understood. It was a story of patience, observation, and the slow, gradual accumulation of wisdom. The ocean's dance was a mystery, but one that could be learned and predicted. This ancient wisdom, passed down through generations, became the foundation upon which future scientists would build. It shows how even the most complex scientific ideas often begin with simple, persistent observation. The enduring mystery of the tides, once attributed to myths, now invites us to delve deeper into the celestial mechanics that orchestrate this grand natural phenomenon. In our next chapter, we'll leave the ancient shores and journey into the minds of early thinkers who dared to question the myths and seek a more scientific explanation for the ocean's timeless gravitational tune. Until then, keep wondering and keep exploring. The ancient world, as we saw, charted the tides with remarkable precision, connecting them to the moon's silent journey across the sky. Yet, the *y* remained elusive, shrouded in myth and practical observation. As civilizations advanced, especially in ancient Greece, thinkers began to seek more rational explanations. The philosopher Aristotle, a giant of early science, turned his keen intellect to the ocean's rhythm. Aristotle meticulously observed the tides in the Mediterranean Sea. He noted their regularity, but also their relatively small range compared to the vast oceans, a crucial detail that would later mislead him. The Mediterranean, being mostly enclosed, experiences very subtle tides. This limited perspective prevented Aristotle from fully grasping the moon's profound influence, leading him to focus on local winds and currents. Far from the Mediterranean, another Greek, Pytheas of Massalia, embarked on an extraordinary voyage around 325 BC. He sailed beyond the known world into the vast Atlantic. On the Atlantic coast, Pytheas witnessed tides of immense scale, far grander than anything seen in Greece. He was struck by their clear correlation with the lunar cycle, specifically the full and new moons. His travels took him as far north as Britain, where he observed that the highest tides occurred twice daily, and their height varied significantly with the moon's phase and position. Pytheas's accurate observations were revolutionary, but they were largely dismissed or disbelieved by scholars back home, who found his tales of distant, grand tides too incredible to accept. Centuries passed. The Romans, practical engineers and navigators, continued to chart tides for their ports and naval movements, but offered little in the way of theoretical advancement. They relied on empirical knowledge. Through the early medieval period, the moon's influence remained a widely accepted, yet unexplained, phenomenon. Tidal prediction continued as a matter of learned experience and local charts. Then came the Renaissance, a fervent rebirth of inquiry. Minds began to question ancient doctrines, fueled by a new spirit of observation and mathematical reasoning. Among these burgeoning intellects was Galileo Galilei, the great astronomer and physicist. He aimed his revolutionary telescope at the heavens, but also pondered earthly mysteries, including the tides. For Galileo, the tides presented a profound intellectual challenge. He sought a purely mechanical explanation, rejecting any mystical or action-at-a-distance influence from the moon. His theory, detailed in his asterisk dialogue concerning the two chief world systems asterisk, linked tides directly to the Earth's motion. He proposed that the Earth's rotation and revolution created a sloshing effect in the oceans. Galileo imagined the ocean basins as large tubs of water. As the Earth spun and moved around the Sun, the water would accelerate and decelerate, causing it to slosh back and forth. He believed that the combined motions of the Earth, its daily rotation and its annual orbit around the Sun, would cause parts of the ocean to speed up and slow down relative to the seabed. However, Galileo's theory predicted only one high tide per day, occurring when the ocean's motion was at its peak. This contradicted the observed reality of two high tides daily in most places. Despite the widespread ancient observations linking tides to the moon, Galileo dismissed this connection. He found the idea of the moon pulling the oceans without direct contact to be occult and unscientific. Galileo, for all his genius, lacked one crucial concept: universal gravitation. Without understanding the invisible force that binds celestial bodies, a complete explanation for tides was impossible. Yet Galileo's attempt was vital. It forced scientists to confront the problem rigorously and highlighted the need for a more comprehensive theory of motion and forces that could apply to both Earth and sky. The challenge of tides became a significant test for the emerging scientific method. It demanded a unifying principle, a single law that could explain phenomena from falling apples to orbiting planets. The ocean's rhythmic movements were not just a local curiosity. They were a global dance occurring across vast distances, seemingly orchestrated by an unseen conductor. The persistent mystery of the tides underscored a fundamental gap in understanding the forces governing both celestial and earthly phenomena. A grand revelation was needed. The stage was now set for a mind capable of seeing the unseen connections, of formulating a universal law that would finally explain the ocean's puzzling ebb and flow. The ancient whispers of the shore had evolved into scientific questions, and the answers were closer than anyone imagined, awaiting the insight of a truly revolutionary mind. The scientific world, still grappling with Galileo's incomplete tidal theory, yearned for a universal principle. The challenge was immense: to find a single force that could explain both the fall of an apple and the grand, swirling dance of the planets. It was a puzzle that demanded a mind capable of seeing the unseen connections. In the quiet academic halls of Cambridge, a young Isaac Newton pursued his studies. He was a man of profound contemplation, his mind constantly seeking the underlying order in the natural world. His era was ripe with intellectual ferment, a time when empirical observation began to merge with mathematical rigor. Legend speaks of a falling apple not as a singular event but as a catalyst for a monumental thought. Newton observed what countless others had, yet he asked a deeper question: if an apple falls to Earth, does the moon also fall towards Earth continuously in its orbit? This simple question bridged the gap between earthly gravity and celestial mechanics. Newton realized that the same force pulling an apple to the ground might also hold the moon in its orbit around Earth and the planets around the Sun. It was a revolutionary unification. Through years of intense focus and intricate calculations, Newton formulated his law of universal gravitation. Every particle of matter, he proposed, attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This elegant law explained why planets moved in elliptical orbits, why comets followed predictable paths, and why objects fell to Earth. It was a single, overarching principle governing motion throughout the cosmos. The universe was no longer a collection of disparate phenomena. With this powerful new understanding, Newton turned his attention to the persistent mystery of the tides. He saw the Earth and Moon not as separate entities, but as bodies interacting through this invisible, omnipresent gravitational force. Previous thinkers had intuitively linked the Moon to the tides but couldn't explain how. Newton showed that the Moon's gravity indeed pulled on Earth's oceans. However, it wasn't a uniform pull across the entire planet. This was the critical insight. Gravity's strength diminishes with distance. This meant the Moon's pull was strongest on the side of Earth facing it, weakest on the side farthest away, and somewhere in between at Earth's center. This difference in pull was the key. On the side of Earth closest to the Moon's gravitational pull is strongest. It pulls the water towards itself more powerfully than it pulls the solid Earth beneath it. This differential pull causes the ocean water to bulge outwards, creating a high tide. On the opposite side of Earth, farthest from the Moon, the situation is subtly different. Here, the Moon's gravity is weakest. The Moon pulls the solid Earth away from the water on that far side, leaving the water to lag behind and bulge outwards. Thus, Newton explained the puzzling observation of two high tides simultaneously, one on the side facing the Moon and another on the side directly opposite. These two bulges are the fundamental expression of the Moon's differential gravitational influence. As the Earth rotates on its axis, every point on its surface passes through these two tidal bulges approximately twice a day. This explains the familiar rhythm of two high tides and two low tides within a roughly 24-hour cycle. This differential pull is what we now call the tidal force. It's not just the absolute strength of gravity, but the gradient of gravity across an extended body. This subtle yet profound distinction was Newton's true stroke of genius regarding tides. This was a monumental conceptual leap. It moved beyond simple attraction, revealing a more complex interaction where the varying strength of gravity across a body causes internal stresses and deformations. The oceans were literally stretched by the Moon's embrace. These revelations, among countless others, were meticulously laid out in Newton's magnum opus, Philosophiae Naturalis Principia Mathematica, published in 1687. It was a foundational text, reshaping the very landscape of natural philosophy. With the Principia, science gained unprecedented mathematical rigor. Newton didn't just propose ideas, he provided the equations that could precisely calculate the forces at play, allowing for accurate predictions. The tides, once mysterious, became quantifiable. Newton's law unified phenomena that had previously seemed unrelated: the fall of an apple, the orbit of the Moon, and the ebb and flow of the tides. It demonstrated the underlying unity of the cosmos, governed by a single, elegant principle. The Moon's long-suspected influence on tides, which Galileo had dismissed as occult, was now explained through purely mechanical, gravitational means. The intuitive link observed by ancient peoples was finally given a scientific foundation. Newton also accounted for the sun's influence. Though much more massive, its greater distance means its tidal force is about half that of the moon. He explained how the alignment of the sun, moon, and earth creates higher spring tides and weaker neap tides. For the first time, scientists could move beyond mere observation to truly predict tidal patterns with remarkable accuracy. This was not just understanding, but mastery, a profound leap in humanity's interaction with the natural world. While Newton explained how gravity worked, the idea of a force acting across empty space without contact remained a philosophical challenge, even for him. He offered no explanation for gravity's cause, only its observable effects and mathematical description. The oceans, once thought to be breathing or moved by deities, were now understood to be dancing to a precise, gravitational tune. Their rhythm was a direct consequence of the cosmic ballet between Earth and its celestial companions. Newton's work marked a new era in science. It was a testament to human intellect, showing how complex natural phenomena could be explained by universal laws derived from careful observation and rigorous mathematics. The mystery began to yield. With gravity's unveiling, the foundational understanding of tides was firmly established. Yet the story didn't end there. The precise nuances of tidal prediction, the influence of coastlines, and the practical applications of this knowledge would continue to unfold, leading to even deeper insights into our dynamic planet. Continuing from Newton's foundational work, the understanding of tides was profound. Yet, even with gravity's unveiling, the ocean's daily rhythm held subtle variations that demanded closer scrutiny. Not every high tide reached the same peak, nor every low tide the same trough. These discrepancies, though minor, hinted at another celestial influence, a secondary conductor in this grand oceanic symphony. The 18th century became a period of meticulous refinement. Scientists, armed with Newton's laws, sought to account for every nuance, every subtle change in the ocean's breath. They knew the moon was the dominant force, but increasingly observations pointed to the sun. While vastly more massive, its immense distance diminished its tidal effect. Newton had acknowledged the sun's role, but its precise contribution to the tidal dance needed to be quantified. It was a subtle, yet significant, gravitational tug. Imagine our Earth nestled between the moon and the sun, each pulling with invisible threads. The strength and direction of these pulls constantly shifted as the bodies orbited. The most dramatic tidal variations occurred when these celestial bodies aligned in specific configurations. This led to the clearer understanding of spring tides. Spring tides happen when the sun, earth, and moon align in a straight line. This occurs during the new moon, when the moon is between the sun and earth. It also happens during the full moon, when the Earth is positioned between the sun and the moon. In both cases, their gravitational forces combine. The moon's primary tidal pull is powerfully reinforced by the sun's gravitational influence. Their combined force creates a stronger deformation of the ocean's surface. This cosmic alignment results in exceptionally high tides and unusually low tides. The difference between the highest and lowest water marks is at its maximum. Mariners and coastal dwellers had long observed these king tides, often associated with the new and full moon, but now the celestial mechanics provided the precise reason. The name spring tide itself offers a clue, referring not to the season, but to the water springing up or springing forth with greater energy. Conversely, when the sun and moon were not aligned, their poles could partially counteract each other. This led to the concept of neap tides. Neap tides occur when the sun and moon are at right angles to each other, as seen from Earth. This happens during the first and last quarter moon phases. In this configuration, the moon's gravity still creates bulges along its axis, but the sun's gravity pulls water away from those bulges towards its own axis. The gravitational forces are essentially working at cross purposes, partially canceling each other out. It's a subtle tug-of-war across the vast oceans. The result is less extreme high tides and less extreme low tides. The overall difference between high and low water is at its minimum during neap tides. This explained why, at certain times of the month, the ocean's rhythmic breath seemed shallower, less pronounced than its usual deep inhale and exhale. The integration of both the moon and the sun's influence was a critical leap. It allowed for far more accurate and nuanced tidal predictions, moving beyond simple observation. Tidal charts became increasingly sophisticated, aiding navigation, port operations, and coastal planning with unprecedented precision. While the general principles were established, the actual behavior of tides is also influenced by local factors: the shape of coastlines, the depth of the ocean basins, and even underwater topography. Scientists like Pierre-Simon Laplace would later build on these foundations, developing more sophisticated mathematical theories to account for these complex interactions. The oceans, once thought to be solely under the moon's command, were now understood to be dancing a grand duet, harmonized by both our closest celestial neighbor and our distant, powerful star. This refined understanding, a testament to persistent observation and mathematical rigor, further solidified humanity's grasp on the cosmos. Yet, the story of tides continued to unfold, leading to even more dynamic insights into our watery world. Newton's gravitational laws provided the blueprint for understanding tides, explaining the moon and sun's combined pull. Yet, as observations grew more precise, subtle discrepancies emerged, hinting that the ocean's response was more intricate than a simple, static bulge. The initial model, often called the equilibrium theory, envisioned the oceans as a perfect, infinitely deep layer of water, instantly conforming to gravitational forces. It was a useful starting point, a conceptual ideal. However, Earth is not a perfectly smooth sphere, and its vast oceans are far from infinitely deep. They are confined within irregular basins, punctuated by continents and varying depths. These real-world complexities meant the equilibrium theory, while elegant, couldn't fully explain the observed timing and height of tides in different locations. The actual ocean behaved differently. A crucial factor missing from the initial equilibrium picture was the Earth's constant rotation. The planet spins rapidly, carrying the oceans with it, yet the tidal forces are exerted by a relatively fixed moon. If the tidal bulges were truly static, fixed directly beneath the moon and on the opposite side, then as Earth rotated, landmasses would simply pass through them. Yet observations revealed that high tides didn't always occur precisely when the moon was overhead. There was often a significant lag, a delay that defied the simple equilibrium model. Furthermore, the shape of coastlines and the varied depths of ocean basins profoundly influenced how water actually moved, creating complex patterns far beyond simple bulges. It became clear that a static equilibrium view was insufficient. The oceans were not merely passive recipients of gravitational pull, they were dynamic systems responding in complex ways. As the 19th century dawned, scientific thought moved beyond static gravitational models, embracing the dynamic nature of Earth's response to celestial forces. The new challenge was to incorporate the physics of fluids, the way water actually moves, into the grand gravitational equations. This required a different kind of mathematical genius. One mind rose to this challenge: Pierre-Simon Laplace, a French mathematician and astronomer of immense intellect. He sought to create a more comprehensive theory of tides. Laplace's groundbreaking work led to the dynamic theory of tides. He recognized that the tidal bulges were not stationary mounds of water, but rather immense, propagating waves. He treated the oceans as a system of waves constantly chasing the moon's position. These waves were influenced not just by gravity, but by the physical properties of the ocean itself. Laplace incorporated the effects of ocean depth. The speed at which a wave travels depends on the depth of the water it moves through. Deeper water allows waves to travel faster. The shape of ocean basins with their irregular boundaries also played a crucial role. These boundaries could reflect, refract, and even amplify tidal waves. Crucially, Laplace also accounted for the Coriolis force, an apparent force resulting from Earth's rotation that deflects moving objects, including vast bodies of water. The Coriolis force subtly steers the tidal waves as they propagate across the globe, causing them to move in complex rotary patterns rather than simple back-and-forth sloshing. The realization was profound. The tidal bulges aren't static piles of water that Earth spins under. Instead, they are effectively waves, constantly propagating across the ocean floor. These waves are constantly chasing the moon's position, attempting to maintain the gravitational equilibrium, but limited by the ocean's depth and the Earth's rotation. This dynamic perspective finally explained why high tides often occurred asterisk after asterisk the moon had passed overhead, or why some places experienced unusually large or small tidal ranges. The ocean's true dance was far more intricate than previously imagined, a complex interplay of gravitational forces, planetary rotation, and the physical constraints of ocean basins. Tidal prediction transformed from a purely gravitational calculation into a complex hydrodynamical problem, requiring sophisticated mathematical tools and a deep understanding of fluid mechanics. Laplace's dynamic theory was a monumental conceptual leap, transforming our understanding of tides from a passive response to an active, wave-like phenomenon. It underscored the Earth's dynamic nature. While the global principles were now clear, the precise behavior of tides in specific harbors and estuaries still held local complexities, awaiting even more detailed observation and computational power. The story of the ocean's dance was far from over. Laplace's dynamic theory had unveiled the grand, wave-like nature of tides. Yet, as the 20th century dawned, oceanographers knew the global models, while powerful, still couldn't predict every local nuance. The real Earth, with its sprawling continents and intricate seafloor, presented a far more complex stage. The oceans were not uniform. A tide that surged dramatically in one bay might be barely noticeable a few hundred miles away. These discrepancies hinted that the land itself, the very shape of the ocean basins, played a profound role in how tidal waves behaved. The scientific challenge shifted. It was no longer just about the moon and sun's pull or even the Earth's rotation. Now, it was about understanding how immense bodies of water, responding to these forces, interacted with the solid boundaries of our planet. Researchers began to view tidal waves not simply as sloshing back and forth, but as vast, rotating systems. Imagine a basin of water set in motion. The water doesn't just move linearly. The Earth's rotation, through the Coriolis effect, compels it into a swirling dance. This insight led to the concept of the tidal wave itself being a rotary wave sweeping around specific points in the ocean. It was a subtle yet crucial distinction from the simpler back-and-forth movement previously imagined. At the very center of these rotating tidal systems lay an intriguing phenomenon, points where the tidal range was virtually zero. These were the nodal points of the ocean's great oscillation. These special locations were termed amphidromic points. Around each amphidromic point, the tidal wave rotates like water swirling down a drain, but on a grand, oceanic scale. At an amphidromic point, the high tide crest and low tide trough effectively cancel each other out. This means that if you stood at such a point, you would experience almost no rise and fall of the sea level, even as immense tidal waves swept around you. The discovery and mapping of these amphidromic points became a cornerstone of modern oceanography. It revealed the true, complex geometry of global tidal patterns far beyond simple bulges. Using increasingly sophisticated data from tide gauges across the globe, scientists painstakingly charted these points and the coastal lines connecting points where high tide occurs at the same time, that radiated from them. The advent of computational models in the mid-20th century revolutionized this mapping. Early computers, though rudimentary by today's standards, could process vast amounts of tidal data, revealing the intricate dance of the oceans. These maps showed how continents acted as immense barriers, forcing the tidal waves to deflect and rotate. A wave approaching a landmass couldn't simply pass through, it had to curve around it, creating these swirling patterns. The very floor of the oceans, with its ridges and trenches, also played a role, subtly guiding and shaping the propagation of these vast waves, adding layers of complexity to the global tidal system. It became clear that each major ocean basin had its own set of amphidromic points, dictating the unique tidal behavior within that region. The Atlantic, Pacific, and Indian Oceans each had their own intricate tidal choreography. Beyond the rotation, another concept emerged: tidal resonance. Imagine pushing a child on a swing. If you push at the right moment in sync with its natural sway, the swing goes higher. This is resonance. Ocean basins behave similarly to a bathtub. Each basin has a natural period at which its water would slosh back and forth if disturbed. This period depends on its size, depth, and shape. If the natural oscillation period of an ocean basin happens to match one of the tidal periods, such as the 42-hour period of the lunar tide, then the tidal effect can be significantly amplified. This explains phenomena like the extreme tides in the Bay of Fundy, where the basin's natural resonance perfectly amplifies the incoming tidal wave, leading to some of the highest tides on Earth. Conversely, if the natural period of a basin is out of sync with the tidal forces, the tidal range can be diminished, leading to very small or even negligible tides, despite the moon's powerful pull. Understanding these resonant rhythms, along with the influence of amphidromic points and continental boundaries, allowed scientists to build far more accurate predictive models for tides worldwide. Modern oceanography, equipped with satellite data, advanced computational power, and a century of accumulated observations, could now map the global tidal dance with unprecedented precision. This detailed understanding was crucial for everything from safe navigation and shipping to coastal engineering and disaster preparedness. The hidden power of surging coastlines was finally being fully revealed. The oceans, once thought to be simply breathing, were now understood to be performing a complex global ballet choreographed by gravity, the Earth's spin, and the very geography of our planet. This intricate understanding of tidal dynamics paved the way for new applications, such as harnessing the ocean's power. The predictable flow of tidal currents could be converted into clean, renewable energy. The journey into the science of tides continued to deepen, moving from global forces to localized interactions, revealing the ocean's dance as a testament to timeless gravitational tunes. But how could this constant motion be effectively harnessed? That was the next frontier. The global ballet of tides, now understood in its intricate wave dynamics, revealed a profound truth. These rhythmic movements held immense, transformative power. It was a force capable of sculpting landscapes and shaping life, a testament to the ceaseless energy of our oceans. We turn our gaze to places where this power is most dramatically displayed. Imagine coastlines where the sea doesn't just rise and fall, but surges with an almost palpable force, reshaping the very contours of the land over millennia. One such place is the Bay of Fundy, nestled between Nova Scotia and New Brunswick in Canada. Here, the unique geography amplifies the oceanic pulse, creating a spectacle of nature's raw power. The Bay of Fundy is renowned for having the highest tidal range in the world. The difference between high and low tide can exceed 16 meters or over 50 feet, the height of a 5-story building. This extreme range is a prime example of tidal resonance, a concept we explored earlier. The natural oscillation period of the Bay of Fundy Basin perfectly aligns with the lunar tidal period. As the enormous volume of water from the Atlantic Ocean rushes into this funnel-shaped bay, the incoming wave grows taller and more powerful, amplified by the narrowing basin. Twice a day, billions of tons of water surge in and out, carving out dramatic cliffs, exposing vast mudflats, and then submerging them again. It is a relentless geological sculptor. Observing the Bay of Fundy reveals the immense energy contained within sustained tidal flow. It's a living laboratory showcasing the sheer scale of the moon's gravitational influence on our planet. Beyond the open coasts, this surging power manifests in another captivating phenomenon, the tidal bore. This occurs when an incoming tide forms a wave that travels upstream against the river current. Tidal bores are relatively rare, requiring specific conditions: a large tidal range at the river mouth, a narrowing, shallow river channel, and a strong incoming tide. As the tide pushes into the river, the water level rises rapidly. If the channel is constricted, this rising water is forced into a concentrated wave, often breaking at its front. Famous examples include the Qiantang River in China, known for its powerful bore, and the Severn Bore in England, which attracts observers eager to witness its dramatic passage. The sound of a tidal bore can be surprisingly loud, a deep rumble preceding the visible wave, as the immense volume of water pushes against the existing river flow. For river ecosystems, the bore represents a sudden, powerful influx of salt water, dramatically changing salinity levels and current dynamics for a brief period. It reveals the dynamic interaction between fresh river currents and the powerful rhythmic forces of the ocean. The river, for a time, bows to the sea's command. Observing tidal bores offers a visceral understanding of the ocean's ability to assert its influence far inland, driven by the same celestial mechanics that govern open ocean tides. Beyond these dramatic displays, tides quietly yet profoundly shape coastal ecosystems. They are the unseen engineers of estuaries, salt marshes, and tidal flats. The rhythmic ebb and flow drives nutrient cycling. As tides flood, they bring in marine nutrients. As they recede, they carry away waste, fertilizing the delicate coastal ecosystems. This constant replenishment supports a rich biodiversity. Estuaries where fresh and saltwater mix are among the most productive ecosystems on Earth, nurseries for countless species. Tides also dictate the migration patterns of marine life. Fish, crabs, and birds time their movements to the tidal cycle, seeking feeding grounds or avoiding predators. The intertidal zone, the area between high and low tide marks, is a harsh but vital habitat. Organisms here must adapt to cycles of immersion and exposure, a testament to tidal resilience. Geologically, tides are relentless sculptors. They erode shorelines, transport sediments, and deposit them elsewhere, constantly reshaping beaches, deltas, and barrier islands. Over vast spans of time, the sustained power of tidal currents carves out unique geological features, from intricate tidal channels in mudflats to massive coastal cliffs. This intricate dance of water and land, orchestrated by the moon's distant pull, reveals how our planet is a constantly evolving system, shaped by forces both celestial and terrestrial. The sheer power of these transformed coasts, from the extreme ranges of Fundy to the daily sculpting of estuaries, prompts a new question. Can humanity harness this relentless, predictable motion? This opens the door to modern applications, a frontier we'll explore next. The dynamic dance of the oceans, propelled by the moon's distant pull, holds a power that sculpts our very planet. But this energy, constantly in motion, isn't without consequence. The immense volume of water shifting across the Earth's surface creates a subtle yet profound effect, one that reaches far beyond the immediate coastline. Imagine the Earth spinning, a vast blue marble in space. As it rotates, the tidal bulges, those immense waves we've discussed, are constantly being pulled by the moon. But the solid Earth beneath them is spinning faster than the tidal bulges can keep up. This leads to a slight lag. The tidal bulges are, in essence, dragged along by the faster spinning Earth, causing them to be positioned slightly ahead of the moon's direct alignment. This tiny offset is crucial. Consider the immense friction generated by these vast bodies of water dragging against the ocean floor and the continents. It's not a frictionless system. This tidal friction acts like a brake, a continuous, subtle resistance to Earth's rotation. Just as a spinning top gradually slows down due to air resistance, the Earth's rotation is imperceptibly decelerating. The oceans, in their relentless pursuit of the moon's gravitational pull, are subtly slowing our planet's spin. This effect is tiny on a daily scale, far too small to notice without precise instruments. But over vast geological timescales, its cumulative impact is profound. It's a testament to how persistent minute forces can reshape celestial mechanics. Scientists, through meticulous study of ancient geological records and fossilized growth rings in corals, have found evidence of this slowing. These growth rings act as natural clocks, preserving the number of days in a year from millions of years ago. Millions of years ago, a day on Earth was significantly shorter than our current 24 hours. The moon's gravitational pull and the resulting tidal friction have been steadily lengthening our days, 1 microsecond at a time. Further evidence comes from historical astronomy. Records of ancient solar eclipses, meticulously documented by civilizations like the Babylonians and Chinese, provide precise timestamps from millennia past. By comparing these ancient observations with modern calculations, astronomers can detect the minute discrepancies caused by the Earth's slowing rotation. The Earth isn't quite where it should be based on a perfectly constant spin. But where does this dissipated energy go? Energy is never truly lost, it merely changes form or transfers. In this cosmic dance, the energy from Earth's slowing rotation is transferred to the Moon. The Moon, feeling the gravitational tug of the tidal bulges that are slightly ahead of it, receives a tiny push. This push, though minute, adds angular momentum to the Moon's orbit. This added angular momentum has a profound effect. It causes the Moon to slowly, imperceptibly move further away from Earth. It's a direct consequence of the tidal interaction. Modern technology, specifically lunar laser ranging experiments, has confirmed this. Scientists bounce lasers off reflectors left on the Moon by Apollo missions and measure the time it takes for the light to return. These precise measurements reveal that the Moon is currently receding from Earth at a rate of about 3.8 centimeters or about 1.5 inches per year. This tiny distance adds up over eons. This means that billions of years ago, the Moon was much closer to Earth and our planet spun much faster. The length of a day would have been considerably shorter, perhaps just a few hours. This ongoing tidal breaking has profoundly shaped the Earth-Moon system throughout its 4.5 billion-year history. It's a continuous, dynamic evolution driven by gravity and friction. The lengthening of our day has, in turn, influenced the very history of life on Earth. Organisms adapted to the changing day-night cycles, and the planet's climate and atmospheric circulation were subtly affected. From a primordial, rapidly spinning Earth with a colossal, nearby Moon to our current, more sedate pace, the tidal forces have been the silent sculptors of our cosmic home. This realization highlights the interconnectedness of our solar system. The ocean's rhythmic breath is not just a local phenomenon but a key player in the grand cosmic ballet, influencing the very fundamental properties of our planet and its companion. The subtle slowing of Earth's rotation and the Moon's gradual retreat are profound consequences of gravity's reach and the relentless interaction between celestial bodies and liquid oceans. It underscores how even seemingly minor forces operating over immense timescales can lead to monumental changes, shaping the environment in which life evolves and thrives. This energy transfer from rotational kinetic energy to orbital energy is a beautiful demonstration of the conservation laws of physics at work on a planetary scale. The quiet pull of the moon, orchestrating the tides, is simultaneously dictating the deceleration of our planet and the slow, graceful retreat of our closest celestial neighbor. It is a timeless, ongoing transformation. Understanding this deep, fundamental interaction between Earth and Moon empowers us to appreciate the subtle forces that shape our world. And in turn, it leads us to ponder how humanity might harness this immense, predictable energy, a challenge for the next chapter. The ocean's rhythmic breath, its ceaseless ebb and flow, has been a source of wonder and mystery for millennia. We've journeyed from ancient observations to Newton's cosmic embrace, understanding how gravity orchestrates this grand dance. But what if this predictable, immense power could be harnessed for our future? In the 21st century, humanity looks to the tides not just as a natural phenomenon, but as a potential wellspring of clean, renewable energy. It's a profound connection between ancient rhythms and future innovation, a testament to our evolving relationship with Earth's forces. One of the earliest and most direct ways to capture tidal power involves massive structures called tidal barrages. Imagine a dam built across an estuary or bay designed to impound large volumes of water. The principle is elegant. As the tide rises, water flows through gates into the basin behind the barrage. At high tide, these gates close, holding the water back. Then, as the tide outside the barrage recedes, a significant height difference is created. This stored water is released through turbines, much like in a hydroelectric dam, generating electricity. The La Rance tidal power station in France, operational since the 1960s, stands as a pioneering example. Its concrete walls have silently generated power for decades, demonstrating the longevity of such a system. The advantage of tidal barrages is their predictability. Unlike wind or solar, the tides follow a precise, known schedule, allowing for consistent energy output, a valuable asset for grid stability. However, their scale also presents challenges. Barrages can significantly alter estuarine ecosystems, affecting fish migration and sediment patterns. The environmental footprint is a critical consideration. These environmental concerns, coupled with the high upfront construction costs, have led researchers to explore alternative, less intrusive methods of harnessing the ocean's dynamic power. Enter the era of tidal stream generators. These devices are akin to underwater wind turbines designed to capture the kinetic energy of strong tidal currents rather than the height difference of the water. They operate entirely submerged, often anchored to the seabed in channels where water flows rapidly. As the tide rushes in or out, the powerful currents spin the turbine blades, generating electricity. This approach offers several benefits. Tidal stream devices have a smaller visual impact as they are largely out of sight. They can also be deployed in a modular fashion, scaled to specific site conditions. Yet, the underwater environment presents its own set of formidable challenges. Saltwater corrosion, biofouling, and the immense forces of the ocean demand incredibly robust materials and sophisticated engineering. Ongoing research focuses on developing more efficient blade designs, durable materials, and advanced mooring systems. The goal is to maximize energy capture while minimizing maintenance and environmental disturbance. Scientists are also working to better understand the interaction between these turbines and marine life. Studies track fish movements and assess any potential impact on local ecosystems, striving for harmony with nature. Connecting these remote underwater farms to the electrical grid is another complex puzzle. It requires specialized subsea cables and reliable transmission infrastructure, often in challenging offshore conditions. The pursuit of tidal energy is a global endeavor with pilot projects and research initiatives spanning continents. From the powerful currents of Scotland to the deep channels of Canada, the potential is vast. Its inherent predictability makes tidal power an ideal complement to intermittent renewables like solar and wind. It can provide a stable baseline for energy grids, smoothing out fluctuations. Innovation continues at a rapid pace, from advanced materials that resist the harsh marine environment to smart turbines that can adjust their pitch to optimize energy capture in varying currents. The ultimate goal is to develop tidal energy solutions that are not only efficient and cost-effective, but also environmentally benign, allowing us to harness nature's power responsibly. This ongoing research and development into tidal energy perfectly embodies our journey. It shows how our increasing scientific understanding allows us to not only comprehend, but also respectfully interact with the Earth's profound and ancient gravitational dance. From the earliest observations of our ancestors to Newton's universal laws, and now to the cutting edge of renewable energy, the story of tides is a continuous narrative of human curiosity and ingenuity. It reminds us that our oceans truly dance to a timeless gravitational tune, a symphony orchestrated by the silent pull of the moon and the distant embrace of the sun. It's a profound connection between the cosmos and our planet. This journey through the science of tides is a journey into the heart of our interconnected universe. It's a tale of patience, observation, and the enduring wonder of discovery, perfect for peaceful contemplation. And so, as the moon climbs high, its quiet pull still orchestrating the world's waters, we find a sense of completion in understanding this ancient rhythm. May its gentle influence bring you calm, and as the moon climbs high, sleep well.